Dawn is the ocean's most fragile hour. The horizon glows with faint orange, but below the surface the world is still blue-black, a chamber of shadows cut only by shafts of silver light that filter through the rolling swells. From within a forest of kelp, a seal begins its morning commute, weaving through the columns like a cautious traveler slipping between city streets at first light. Its body arcs and bends with liquid grace, each movement sending ripples of pressure that broadcast to the unseen. It swims across what appears to be an illuminated disc suspended in the gloom, a trick of optics that divers call Snell's window. To the seal, it is just the boundary between its hidden world and the blazing sky above. To the predator lurking below, it is something more, a portal, a perfect frame in which silhouettes betray themselves, a screen upon which the seal's outline is painted in unavoidable clarity. Snell's window is the key to one of the most precise ambushes in nature. Because of the way light bends when it passes from air into water, a submerged observer sees the entire sky compressed into a glowing circle about twice the width of an outstretched arm. Outside that circle lies only darkness, the fractured mirror of the seabed above, or the deep blue void of refracted angles. It is a physics trick, but for the great white shark it is more than science, it is strategy. The shark hovers just below the threshold, angled so its pale belly merges with the glare of the sky, while its charcoal back dissolves into the abyss beneath. To any upward glance from the seal, the shark is invisible, absorbed into the geometry of light and shadow. To the shark, however, the seal is perfectly outlined against the radiant disk. Predator and prey are inhabiting the same field, but only one sees the rules of the game. The shark begins its ascent not with reckless speed, but with patience. Its massive body, up to the length of a small car, is streamlined not for endurance alone, but for bursts of acceleration. The great white's pectoral fins, stiff and scythe-shaped, act as both rudders and lift planes, trimmed at just the right angle to funnel the body into a vertical strike. Its musculature is a network of red fibers interlaced with white, designed not just for power, but for efficiency. Hidden beneath its thick dermal layers, an extraordinary adaptation fuels the coming attack, regional endothermy. Unlike most fish, which are at the mercy of surrounding water temperature, the great white carries a system of heat exchangers known as rete mirabile, wonderful nets that allow it to elevate the temperature of key tissues. Blood coursing from powerful swimming muscles is warmed and redirected to the eyes and brain, keeping neural signals sharp and vision keen even in cold water. When the strike comes, milliseconds will count, and this thermal advantage ensures that its reactions are as crisp as the surface glare above. The seal is not oblivious. Evolution has armed it with countermeasures. Its dark back and pale underside echo the same countershading as the shark's, camouflage for both above and below. It zigzags in erratic paths, knowing instinctively that straight lines invite predictability. It hugs the kelp where fronds mask its outline, darting through shafts of shadow that confuse shapes and break continuity. Seals have lived with white sharks for millennia, and their nervous systems are tuned to flickers in the periphery, sudden shifts in pressure, the faint whisper of a predator's tail. But here, in open water, away from the thickest kelp, the seal commits its mistake. It drifts too long across the glowing disk, framed by physics, betrayed by geometry. The shark tilts its snout slightly, calibrating like a missile. Its eyes, unblinking black mirrors, lock on the silhouette. Its tail, nearly half the body's length, sweeps once, then twice, each stroke bending the water like steel cables pulling a catapult taut. From stillness, the shark accelerates in a vertical surge, body trembling with unleashed energy. Water peels away from its flanks, vortices spiral off its trailing fins, and microbubbles hiss from the sudden collapse of pressure. The seal reacts. There is always a reaction, but the mathematics favor the predator. The window narrows as the shark rises. The seal's options dissolve into fragments of seconds. Turn left, and the pectorals guide the shark's arc. Turn right, and the thrust adjusts with imperceptible fin flicks. Upward is the trap itself. Downward is too late. The kill is not brute force alone, it is an optical equation solved from below. When the shark breaches, the sea surface detonates. A geyser of spray erupts as tons of muscle and cartilage pierce the air. For a moment, gravity suspends predator and prey in tableau. The shark's jaws yawning wide, rows of serrated teeth gleaming against the morning light, the seal twisting in a last desperate contortion. Then impact, bone against bone, flesh against enamel, water collapsing back into its basin. Not every strike is fatal. Many seals escape, bearing scars that testify to close calls, the deep arcs of shark teeth etched into their flanks. These survivors become faster, warier, ghosts that remind the colony of the cost of complacency. But enough strikes succeed to fuel the shark, to maintain its role as the architect of fear along the kelp's edge. This scene plays out thousands of times each year along coasts where kelp meets open ocean, particularly in places like South Africa's False Bay or California's Channel Islands. Researchers who observe the patterns notice the choreography, the preference for dawn and dusk when light angles sharpen silhouettes, the tendency of sharks to wait just meters below Snell's window, never revealing themselves until the last moment, the consistency of vertical bursts aimed directly at the disc. It is not randomness. It is precision honed by millions of years of evolutionary trial, refined through failures and successes across lineages of ancestors. The shark is not solving equations consciously, but its body and senses are tuned to the geometry of light, the refraction of water, the thermal balance of muscles, and the physics of motion. Every element contributes to the strike. Why then do seals still venture into open water when such risks await? Because life demands it. The kelp forest shelters them but does not feed them in full. To grow, to nurse their pups, to sustain colonies, they must hunt fish and squid that gather beyond the shelter of fronds. They gamble survival against opportunity, speed against stealth. And though many fall, their populations persist, balancing predator and prey in a cycle where neither side can wholly triumph. If sharks consumed every seal, they would collapse their own food supply. If seals outpaced every shark, the predator would vanish, and with it, the pressure that sharpens the seal's vigilance. The equilibrium is brutal, but it is balanced nonetheless. Viewed from a human lens, the breach is spectacle. Jaws, blood, and spray captured in freeze frames. But underneath it is physics at work. Snell's window compressing vision, countershading dissolving forms, endothermic muscles igniting acceleration, prey tactics deflected by split-second timing. It is not chaos. It is the ocean running a formula written in light and shadow, solved with muscle and teeth. In this equation, hesitation is death and precision is survival. The Great White Strike reminds us that the sea is not an endless void, but a theater of optical illusions, thermodynamic advantages, and behavioral gambits. Every hunt is a test of biology against physics, prey instincts against predator calculations. When the shark rises like a missile through the glowing circle, it is more than a predator feeding. It is nature proving once again that survival is not about strength alone, but about knowing how to read the rules of light, water, and time, and how to exploit them in the final, decisive second. The ocean at night is a place of contrasts. Above, the moon casts silver streaks across the waves, but below, in the narrow throat of a reef pass, darkness reigns. Coral heads fade into silhouettes, and the sand is no longer golden but a pale ghostly sheen, broken only by drifting clouds of plankton and the faint sparkle of bioluminescent flashes. It is here, in these passages between lagoon and open sea, that the tiger shark begins its patrol. Broad-bodied, blunt-snouted, and bearing the faint shadow stripes that give it its name, the shark does not move with the ceaseless urgency of a tuna or the explosive restlessness of a great white. It moves with deliberation, with a patience that conceals calculation. Its body sways side to side in a zigzag, sweeping across the current like a pendulum measuring time. To the casual eye, it seems aimless. But this motion has purpose. It is a predator reading a road that few others can sense. The current carries more than water. It carries stories. A wounded parrotfish bleeding slightly from a reef scrape, a sea turtle oozing faint oils from its carapace, a grouper releasing gametes into the night tide. Each event leaves a chemical footprint. Molecules drift, dilute, disperse, and twist with the eddies of moving water. To most creatures, they are invisible whispers too faint to decode. To the tiger shark, they are pathways, messages written in chemistry. The shark's nostrils set wide on its snout are not for breathing, they are portals for smelling. Each is connected to labyrinths of folded tissue lined with olfactory receptors. When water enters, molecules bind and signals race to the brain. Because the nostrils are separated, the shark achieves something akin to stereo hearing, but in scent. One nostril may pick up a molecule fractionally earlier or stronger than the other. That difference is enough to establish direction, a gradient the shark can follow. It is why the shark weaves. Crossing back and forth through the current, it compares signals, testing strength, shifting its course by degrees. Much like a bloodhound casting across a field to catch the line of a trail, the tiger shark casts across its liquid world to reacquire the invisible plume. When it finds the road again, its tail stiffens, its body aligns, and it glides forward with renewed intent. If it loses the trail, it zigzags once more, patient, methodical, and tireless. The reef pass sharpens this hunt. These narrow channels funnel water from the lagoon to the open sea, especially on a falling tide, concentrating both prey and scent. A turtle leaving the protection of shallow seagrass to forage in deeper water may slip through this corridor. So too may schools of jacks or mullet pressed by the shifting tide. To the tiger shark, these passes are choke points where odds of encounter increase. Energy economy drives its choice. A predator that grows as long as a small car and weighs more than half a ton cannot afford to squander effort. It is a scavenger when opportunity offers, consuming carrion or discarded fish guts, but in the funnel of the reef pass it becomes an ambusher, a strategist who lets water do the work of delivery. The night magnifies its advantages. Fish that rely on vision are less vigilant in low light. Turtles who must surface for air are silhouetted against the moonlit surface. But most of all, the cloak of darkness enhances the shark's second sensory weapon, electroreception. Along its snout and lips lie pores, each filled with a conductive gel. These are the ampullae of Lorenzini, a sensory array so fine that it can detect electrical fields measured in billionths of a volt. Every muscle contraction, every heartbeat, every flicker of nerve activity generates a field. To the shark, approaching within a few body lengths of a hiding prey is like stepping into a room filled with faint but distinct signals. Imagine the final approach. The scent road has been followed to its narrowing end. A turtle rests near the sandy bottom, lungs filled, flippers tucked loosely, unaware of the predator homing in. The shark cannot see the turtle clearly yet. Light is sparse, outlines faint, but it does not need to. The ampullae whisper of rhythm, a heartbeat pulsing slow and steady, a faint current flowing across a buried nerve. As the shark closes, the signals grow stronger, mapping not just the presence, but the orientation of its target. In these last meters, chemistry yields to electricity. The shark corrects its aim with minor adjustments of pectoral fin and tail beat. Then, in a sudden kink of the body, it snaps to the side, jaws opening in a wide arc. The turtle thrashes, sand billows, but the ambush has already found its mark. Not every hunt ends in capture. Prey are not defenseless. Turtles possess shells that can resist crushing bites, and many fish erupt into sudden bursts of speed, vanishing into reef crevices where the shark's bulk cannot follow. But the tiger shark is resilient in failure. Energy expended in short ambushes is offset by its opportunistic diet. When live prey proves elusive, it turns scavenger again, consuming carcasses, fish offal, even seabirds or floating debris. This broad palette, more varied than almost any other shark, ensures survival where specialists might falter. But the reef pass ambush demonstrates that its reputation as a lazy scavenger is misleading. The tiger shark is both opportunist and tactician, capable of patience and precision when circumstances favor efficiency. Some scientists suspect there is more to its navigational prowess than smell and electricity alone. Evidence suggests that tiger sharks, like many migratory fish, may possess a magnetic sense, an ability to detect Earth's field lines as a kind of map. Tagged individuals have been recorded crossing vast ocean expanses, swimming straight between island groups hundreds of kilometers apart without veering. In reef systems dotted like stepping stones across the Pacific, this ability could guide them from one pass to another, revisiting productive ambush corridors with uncanny accuracy. If smell is the close-range compass and electricity the final lock, magnetism may be the chart that carries them across the wide seas in between. The balance they strike between energy and reward reflects a truth of predator life. Efficiency is as vital as ferocity. A tiger shark cannot sprint endlessly like a tuna, nor can it specialize in a single tactic like the white shark's breach. Instead, it economizes. A zigzagging patrol at a reef pass costs little energy and offers steady chances. A strike powered by chemical and electrical information minimizes wasted lunges. Its physiology supports this strategy. With a slower metabolism than many pelagic hunters and the ability to scavenge when needed, it is a predator designed for persistence, one that thrives not through drama but through steady, adaptable tactics. For the diver watching from the safety of a reef shelf, the sight is eerie. A shadow slides across the sand, faint stripes flickering in the moonlight. It turns, crosses, turns again, like a ghost testing boundaries. Then it stiffens, angles sharply, and vanishes into the pass. Somewhere ahead, unseen, a chemical road has become an electrical certainty. The predator has read the invisible script and moved to its final act. The tiger shark reminds us that hunting is not always spectacle. Sometimes it is patience, an invisible dialogue with molecules drifting in water, with currents that carry information as surely as they carry fish. The shark does not see a trail, yet it follows one. It does not hear a heart, yet it locates one. Its survival is built on the fusion of chemistry, electricity, and perhaps even magnetism. A suite of senses so refined that what appears to us as empty water is, for the shark, a landscape filled with roads, signals, and hidden destinations. And so, in the dark throat of the reef pass, the tiger shark teaches a simple lesson. In the ocean, survival belongs not only to the swift or the strong, but to those who can read what others cannot. For this striped hunter, chemistry gives the direction, and electricity gives the final answer. The flow drifts like a fragment of broken continent, its edges melting into the frigid sea. On its surface lies a solitary seal, a mottled smear of life sprawled on white ice, half dozing, half vigilant. The air is sharp, the silence broken only by the distant calls of seabirds. Then the water stirs. Just beyond the flow's shadow, 3 dark dorsal fins rise in perfect sequence, cutting through the surface with the precision of synchronized blades. Orcas, black and white shapes so stark against the blue that they appear sculpted by contrast itself. They are not here to circle aimlessly. They are here to engineer the sea. The trio dive in unison, their bodies arcing downward before curving back toward the surface. Momentum builds with every tail beat, each animal angling not for the seal directly, but for the ice. Their goal is not collision. It is construction. With mass behind them and water as their medium, they create a moving wall. Physics takes over. As their bulk pushes upward, they displace enormous volumes of water, 3 surges coalescing into one. The wave climbs, smooth at first, then curling as it reaches the shallow undercut of the flow. The seal's eyes widen as its resting platform shudders. The wall of water crashes onto the ice, tilting it just enough that the seal slides helplessly into the sea, directly into the jaws of waiting predators. This is not brute force. It is engineering. Wave-making is one of the orca's signature hunting techniques, and it demonstrates a rare truth in the animal kingdom. These predators weaponize the medium they inhabit. By manipulating momentum, speed, and the angles of approach, they can amplify each other's output, creating constructive interference where multiple waves stack into one. It is the same principle that shapes tsunamis or rogue waves in the open ocean, but here it is harnessed with deliberate intent. To see a pod of orcas dislodge prey from ice is to watch predators using the physics of fluid dynamics as if it were instinct, But behind instinct lies culture. Young orcas learn this method not by chance, but by imitation, watching elders perform it until the rhythm of approach and retreat is etched into their own hunting repertoire. Not all waves are built to dislodge. Some are built to stun. In temperate seas where fish school densely, orcas turn their tails into shockwave generators. A tail slap may appear to the human eye as little more than a splash, but its true force lies beneath the surface. When an orca swings its muscular tail flukes in a sudden arc and strikes the water flat, the impulse generates a pressure pulse that travels faster than the eye can track. Small schooling fish caught within its radius are not merely splashed, they are concussed. Their swim bladders rupture, their lateral lines are overwhelmed, and they float dazed or motionless, suddenly transformed from agile prey into easy pickings. The splash is theatre. The physics below are the kill. Water, then, is not just habitat for orcas, it is a tool. But the weaponization of water does not end at waves or tail slaps. Orcas also command the medium of sound, and here lies their most advanced weapon. Sound travels more than 4 times faster in water than in air, and with less loss over distance. Orcas exploit this with echolocation clicks, whistles and pulsed calls that can fill an entire bay. Their heads house a fatty organ known as the melon, which focuses sound beams like a lens, allowing them to scan their surroundings in 3-dimensional acoustic images. A fish's scales, a seal's lungs, even the contours of ice or the slope of a sandy bottom, each reflects sound differently, painting the orca's perception of the world. But echolocation is not merely for perception. In coordinated hunts, it becomes the thread that weaves a pod into a single organism. By timing their calls and clicks, orcas synchronize movements without needing to see one another. One drives a shoal of herring into a ball while others circle it with lines of bubbles. The timing of a click tells the others when to close in, when to strike, when to slap the water. It is communication layered onto sensation, strategy transmitted at the speed of sound. To watch a pod hunting is to watch distributed intelligence, each individual making decisions in fractions of a second, yet those decisions folding seamlessly into the collective effort. Cultural diversity makes this more fascinating still. Not every pod uses the same playbook. Along the Antarctic ice edges, waves are the chosen strategy. In Norwegian fjords, orcas herd herring into dense spheres known as bait balls, then take turns slapping with their tails to incapacitate dozens at once, a method called the herring carousel. In the Pacific Northwest, resident pods focus almost entirely on salmon, timing their movements with seasonal runs and communicating with dialects distinct to their community. Transient pods in the same waters specialize in marine mammals instead, using stealth and silence where their fish-eating relatives broadcast loudly. These differences are not genetic, they are cultural, passed from generation to generation like oral histories. Each pod has its own traditions, honed by environment, prey type, and social learning. The seal on the floe experiences only the end result, a sudden engineered wave that turns ice into trap. But for scientists, each such hunt is evidence of a predator whose strategies are as varied as they are deliberate. Few creatures demonstrate such plasticity. An orca born into a pod that hunts fish will learn bubble nets and carousel tactics. One born into a mammal hunting pod will learn to stalk silently and to use wave strikes. Switch the calves and they adopt the new culture, proving that these are not hardwired instincts, but learned behaviors. It is in effect a transfer of technology, hunting techniques as cultural artifacts. The power of synchronization cannot be overstated. When 3 orcas align to build a wave, their timing must be within fractions of a second to prevent the water from dispersing in chaotic turbulence. When a pod encircles herring, their bubble lines must be released in precise arcs, or the fish escape through gaps. The ability to phase their actions so perfectly relies on not only acute sensory perception, but on social cohesion. Pods are families, sometimes numbering 20 or more individuals, bound by matrilineal lines and lifetimes spent in one another's company. This stability allows for the deep trust necessary to execute maneuvers where any failure could scatter prey or waste energy. Energy, after all, is the equation beneath every tactic. A wave that dislodges a seal prevents the need for a chase across open water. A tail slap that stuns multiple fish yields a higher return for the effort expended. Sound used for coordination minimizes wasted lunges and collisions. Even in their most spectacular hunts, orcas are accountants of energy, calculating implicitly how best to convert effort into calories. It is this efficiency, married to adaptability, that cements their place as apex predators in every ocean they roam. Yet for all their power, orcas are not invincible. Changes in prey availability due to overfishing, climate shifts, or habitat loss can disrupt the cultural playbooks they rely on. A pod that specializes in salmon will struggle if runs collapse. One that depends on ice flows for wave hunting may find fewer platforms as polar regions warm. Their intelligence and flexibility offer resilience, but culture, once broken, can vanish. Conservationists now see orcas not only as animals to protect, but as carriers of knowledge, repositories of traditions that, if lost, cannot be recreated by biology alone. Back at the floe, the seal is gone, the ice rocking gently in the aftermath of the engineered surge. The orcas regroup, their breaths erupting in misty plumes against the polar air. They glide side by side, a family moving as one, each individual's success inseparable from the group's coordination. They have turned water into weapon, sound into language, culture into strategy. In doing so, they remind us that the ocean's most formidable hunters are not merely defined by muscle or teeth, but by their mastery of physics, acoustics, and social learning. Orcas embody the idea that power is not always about direct force. Sometimes it is about using the world around you, waves, pulses, phases of sound, as tools to bend the environment into compliance. They are predators who transform the sea itself into an ally. They do not just live in water. They think with it, move with it, and when needed, weaponize it. In the end, they show us a truth both humbling and awe-inspiring. The apex predator of the sea is as much an engineer as a hunter. In the deep mid-water, the color drains from the ocean until it becomes not blue but black, a void unbroken by sun or star. The surface is more than a kilometer above, and the seafloor remains an unlit continent somewhere far below. Here, suspended between two worlds, hangs the sperm whale. It is a body built for extremes, long as a bus, heavy as 50 tons, yet capable of slipping into the silent stillness of this abyss with the composure of a shadow. Its massive head, a block that makes up nearly a third of its body length, is not just architecture, it is an instrument. Inside lies the organ that gives the species its name, the spermaceti sac, a cavern filled with oil and waxy fluid, flanked by air-filled chambers and connective tissues. Together they form something unique in the animal kingdom, a living acoustic lens. The whale is not searching with eyes. At this depth, vision is a useless sense, reduced to vague impressions of bioluminescent glimmers. Instead, the whale searches with sound. From its head issues a click, metallic, sharp, like the crack of a hammer on iron. Then another, a train of pulses fired into the darkness. The clicks race outward, beams sharpened and focused by the spermaceti organ, funneled forward in a cone. Low-frequency clicks can travel kilometers, painting outlines of distant ridges or scattering layers, while higher frequencies provide the fine detail needed when prey comes into range. The whale modulates frequency with ease, shifting from long-range sonar to close-range targeting, like a submarine operator adjusting instruments. Out in the darkness, something stirs. A squid, mantle rippling, drifts among the layers of zooplankton that form the vast biological boundary known as the deep scattering layer. This layer is one of the ocean's greatest spectacles, a shifting mirror of life that rises toward the surface at night and sinks into the depths by day. Billions of organisms, lanternfish, shrimp, gelatinous forms, move in unison, creating what is effectively a living curtain. To predators, it is both opportunity and camouflage. To the squid, it is a hiding place, its silhouette fractured by the surrounding chaos of drifting bodies. But the whale is not fooled. Its sound beams slice through the scattering layer, registering echoes with astonishing precision. Every returning pulse maps a world we cannot see. The hard reflection of a squid's cuttlebone, the softer shimmer of tissue, even the subtle ripple of a tentacle in motion. The clicks quicken. What was once a slow, methodical rhythm becomes a tighter sequence, each pulse arriving more rapidly. Scientists call this a creak, the moment when the whale closes on its target, shifting from long-range surveillance to high-resolution strike. Each creak is a flood of acoustic information. The whale can tell not just that the squid is there, but how it is moving, whether it is turning or attempting to flee, perhaps even the rate at which its mantle pulses with each jet of water. To the squid, the clicks are sound without meaning. To the whale, they are vision, vision sculpted from echoes, more vivid than sight could ever be in this eternal night. There is debate among researchers about whether these clicks do more than paint a picture. Some argue that at close range, the power of the pulses may be enough to stun prey, overwhelming sensitive organs, or disorienting with sheer acoustic force. Divers who have felt the strike of a sperm whale's click against their chest describe it as like being thumped by an invisible fist. Yet definitive proof of stunning remains elusive. What is certain is that the creak is the final phase before the strike, the narrowing of distance until predator and prey are locked together in sound. The squid senses the approach, jetting in sudden bursts, turning at the last instant. Its chromatophores flash in agitation, shifting color in a futile display against a hunter who cannot see color at all. But the whale is already within reach. The creak tightens further, clicks blurring into a rapid buzz. In the final meter, the whale is guided not by vision, not by chance, but by the sheer density of acoustic information. Its jaws open, lower teeth fitting into grooves in the upper jaw like the teeth of a trap, and the suction of its gulp drags the squid into darkness. What began with a click ends with a capture. This reliance on sound is not just an adaptation, it is the essence of sperm whale survival. These giants dive deeper and longer than almost any mammal, plunging for more than an hour into depths that would crush unadapted lungs. To conserve oxygen, their heart rates slow. Blood is rerouted to critical organs, and muscles endure on stored myoglobin reserves. Eyesight fades into irrelevance. But sound, unaffected by the absence of light, becomes the one constant thread connecting them to their environment. Through clicks, they map entire seascapes, track prey migrations, and even communicate with one another across vast distances. The ocean itself provides highways for their calls. Layers of water at specific temperatures and salinities form channels where sound can travel extraordinary distances with minimal loss. Known as the SOFAR channel, this phenomenon allows low-frequency calls to propagate for hundreds, even thousands of kilometers. Sperm whales may use this acoustic highway to remain in contact with pod members spread across enormous expanses of ocean, coordinating not just hunts, but the slow, nomadic journeys of their kind. A click in one basin can be answered by another far beyond the horizon, a dialogue stitched across the globe by physics itself. Each hunt is not just a meal, but part of a larger ecological ballet. By preying on squid, sperm whales influence the dynamics of the deep scattering layer, exerting pressure on species that in turn consume plankton and smaller fish. Their feeding habits ripple through the food web, shaping patterns that extend upward even to surface fisheries. And when whales die, their bodies fall as whale falls to the abyssal plain, providing entire ecosystems with decades of sustenance. Even in death, their lives remain bound to the deep, cycling nutrients from surface to seafloor in ways no other predator can. The story of sperm whales is also a story of cultural inheritance. Different populations use different click patterns known as codas to identify themselves, much like dialects in human languages. These codas are not used for hunting, but for social cohesion, a way of declaring belonging and heritage. A calf growing within a pod learns not just how to dive, how to breathe at the surface, or how to follow a click train into the abyss, but also how to speak its family's dialect. This shared language allows pods to recognize allies, exchange information, and perhaps even transmit traditions that outlive individuals. And so the hunt of a single squid in a dark water column is more than an isolated act. It is a window into an evolutionary strategy that redefines what it means to sense the world. Where our species trusts sight above all, the sperm whale trusts echoes. Where we see light, it hears reflections. For it, the sea is never empty. Every click sent and received reveals structure, motion, and opportunity. The abyss is not blind, it is illuminated by sound. Back in the mid-water black, the whale lingers after its strike. Another click pulses outward, then another. The curtain of the scattering layer shifts with faint echoes. New silhouettes emerge, drifting, fleeing, or holding still. The hunt will continue, because a body of such mass requires hundreds of kilograms of prey to sustain. But for each encounter, the process repeats: click, creak, capture. It is a rhythm written into the whale's biology, a song of survival sung in pulses. In this realm where light is absent, it is sound that reigns supreme. The sperm whale, armed with its living acoustic lens, transforms the void into a world of vivid geometry, of moving shadows sculpted from echoes. And in that final moment, as the creek collapses into a buzz and the squid makes its desperate turn, the outcome is already written. In the abyss, sound is vision, and the last meter is decided not by sight, but by the buzz. The sun lies high above the shallows, its rays scattering across turquoise water so bright it seems almost translucent. The sandy bottom shimmers in a heat-like haze of refracted light, while seagrass patches ripple in the current. Into this stage glides a bottlenose dolphin, sleek and silver-grey, its dorsal fin slicing cleanly through the rippling surface before it arcs back under. To the casual eye, it seems playful, an agile shadow meandering across the flats. But to the fish hiding nervously in the shallows, this predator is anything but whimsical. The dolphin is here to build walls where none exist. A sudden flick of its tail sends a column of sand spiraling upward, and in seconds the water begins to cloud. The dolphin turns tightly, circling with deliberate precision, releasing jets of bubbles from its blowhole as it moves. Within moments, the choreography is clear. The animal is not chasing prey in open water, but constructing a trap. A ring forms, a perfect circle of silt and bubbles closing around a school of fish. To the human eye, the barrier looks fragile, an ephemeral haze. But to the fish inside, it is an impenetrable wall. Their instincts, honed over millions of years, scream at them to avoid turbidity. A cloudy patch of water could hide an ambush, a predator, or a deadly hazard. They leap away from the murk toward the only apparent escape, the center of the ring. Waiting there is the dolphin, jaws parted in perfect timing. One snap, and the invisible maze has claimed its victim. This tactic, mud ring feeding, is one of the most spectacular examples of how dolphins manipulate physics to their advantage. By stirring sediment and adding bubbles, they weaponize the very medium in which they live. What appears to us as improvisation is, in reality, a technique passed through generations, a form of cultural learning. Some pods in Florida are famous for this behavior, but it is not universal. It spreads locally, mother to calf, pod to pod, like folklore retold with practical purpose. What is most striking is how the fish react. To them, the ring is not just water and sand, but a structure, a wall their instincts refuse to cross. It is a reminder that perception, not reality, defines survival. The dolphin has learned to exploit that gap. Mud rings are only one of the many walls dolphins construct. In deeper waters, groups turn to bubble curtains. By exhaling streams of bubbles while circling schools of fish, they form shimmering cages that enclose prey. Light scatters chaotically through the bubbles, confusing visual cues and creating the illusion of a barrier. Fish, confronted with what seems like an impassable screen, bunch together tightly. In their panic, they consolidate into dense balls, exactly the shape that makes them easiest to harvest. Once the ball is compact enough, dolphins take turns slicing through it, each individual surging in for a mouthful before rejoining the circling team. It is cooperation shaped not by brute force, but by manipulation of sensory perception. The prey see walls that do not exist, and their reactions make those walls real. Under the tangled roots of mangrove forests, dolphins employ yet another strategy. Here the water is narrow, visibility is poor, and prey such as mullet and small snappers hide among roots and fallen branches. Chasing them directly would be energy-intensive and risky. Instead, dolphins use percussion. With a sharp slap of the tail or a forceful kerplunk of their bodies against the surface, they send shockwaves reverberating through the shallow channels. The sudden pulse of sound and spray startles fish from their hiding places. Many species have a reflexive startle response to loud disturbances, bolting from cover into open water. In that instant of panic, the waiting dolphin claims them. The kerplunk is part sound, part visual flash, part pressure wave, a multisensory assault that turns concealment into exposure. What binds these different techniques together is not the form of the wall, but the concept of control. Dolphins do not simply chase, they shape. They exploit the physics of water, the instincts of prey, and the synchrony of their own pods to redraw the battlefield. To understand how, one must also understand their communication. Timing is everything. When a pod coordinates to build a bubble, curtain, or ring, each individual must align movement to the second. This is where echolocation and calls enter the picture. Dolphins emit high-frequency clicks that bounce off prey, each echo returning data on distance, density, even the orientation of fish. But these clicks are not only for the individual, they become shared cues. A sharp burst here, a whistle there, tells companions when to surge, when to encircle, when to attack. The efficiency of this communication is amplified by the properties of sound underwater. Because sound travels faster and farther in water than in air, dolphins can relay information almost instantaneously across the pod. What might appear as telepathy from above is, in truth, a web of acoustic signals timed with millisecond accuracy. It is why timing, not sheer speed, gives dolphins their edge. Fish may outswim a dolphin for short bursts, but they cannot outmaneuver a strategy where every escape route has been calculated and closed before the chase begins. The cultural aspect of these techniques cannot be overstated. Just as different orca pods develop unique hunting cultures, dolphin pods exhibit regional specializations. Some communities perfect bubble nets, while others rely on kerplunking. In certain bays, mud ring feeding is an art form refined over decades. Young dolphins learn by observation, practicing clumsy circles until they master the hydrodynamics of sediment manipulation. Such transmission of knowledge transforms a hunting tactic into tradition. In this way, dolphins are not only predators but teachers, their societies repositories of ecological intelligence. The walls they create are not without cost. Stirring sediment or producing bubble nets requires energy. Tail slaps strong enough to produce kerplunk pulses are physically demanding, yet the payoff outweighs the expenditure. By concentrating prey, these techniques increase capture rates, ensuring a higher return on investment. In ecological terms, it is efficiency elevated to artistry. Instead of endless pursuit, dolphins manipulate conditions so that prey funnel themselves toward waiting mouths. Consider how this shapes entire ecosystems. Fish populations respond not just to predation pressure, but to the psychological landscapes predators impose. A school harassed into tighter formations becomes easier prey for seabirds above, linking aerial and aquatic hunters in indirect alliances. Sediment disturbed in mud ring feeding exposes invertebrates to other foragers. By creating invisible walls, dolphins influence not only their own meals, but the behavior and survival of countless other organisms sharing the shallows. They are ecosystem engineers as much as they are hunters. There is also irony in how walls define predator and prey. Humans build nets, cages, and pens to trap fish, using material barriers. Dolphins build none, yet achieve the same ends by sculpting perception. Their tools vanish as quickly as they appear. No rope is left behind. No trap remains after the hunt. What endures is only the knowledge carried forward, the memory of prey forced to leap into jaws because instinct misread illusion. It is a form of mastery that feels almost architectural, except the structures exist only for moments, dissolved by currents once the meal is done. The dolphin surfaces for air, exhaling with a puff that sends mist into the warm air, before diving once more to patrol the sandy flats. Somewhere beneath, another school of fish hides among seagrass. The cycle will repeat, a wall drawn in mud, a curtain cast in bubbles, a percussion pulse under mangrove roots. Each is an act of transformation, turning the openness of water into a maze of dead ends. For the fish, every path looks like salvation until the last moment. For the dolphin, every wall is an invisible lever shifting the odds towards certainty. In the end, these predators remind us that survival does not always belong to the fastest or the strongest. Sometimes it belongs to those who can rewrite the rules of perception, who can draw boundaries where none exist. Dolphins have mastered the art of building walls you cannot see, and in doing so, they have redefined what it means to be a hunter in the fluid, shifting theater of the sea. Beneath a ledge of reef, where the afternoon light fractures into rippling shafts of blue and gold, a shadow shifts. At first it seems no more than a ripple of current or the swaying of algae, but then it expands, unfurling into something with intention. An octopus emerges slowly from the crevice, its body flowing like liquid muscle. Its skin pulses once, changing from mottled rock to smooth sand, then darkening again into algae green. To watch it is to witness the ocean's most gifted illusionist preparing for a kill. The octopus moves not with the rigid efficiency of fish, but with a fluidity that defies prediction. Each of its 8 arms explores the substrate independently, the suckers rolling like tiny mouths along coral, sand, and shell. These suckers are not passive anchors, they are sensors, tasting and touching at once. A single sucker can detect minute traces of chemical residue left by prey, identifying whether a crab passed here minutes ago or whether a fish darted into a crevice seconds before. With hundreds of suckers working simultaneously, the octopus creates a chemical map of its environment, an invisible trail drawn across the reef. It is not sight alone that guides the hunt, but a kind of tactile tasting of the world, an extra sense spread across the length of every arm. Yet what makes this system remarkable is that not all decisions flow back to the central brain. Unlike vertebrates, where the brain dictates the movement of limbs, the octopus distributes control. Each arm houses its own clusters of neurons, capable of making local decisions without waiting for instructions. When an arm probes into a crevice and detects the faint chemical trace of a crab, it can adjust its grip, test the opening, and decide whether to push deeper or retract, all while the main brain orchestrates the larger hunt. This distributed intelligence is what gives the octopus its uncanny fluidity, its ability to seem both coordinated and chaotic, as though it were 8 minds tethered to one. Now the octopus finds its quarry. A crab lurks beneath a stone, legs folded tight against its carapace, antennae twitching in faint awareness of danger. For most predators, the rock would be a shield too solid to overcome. But for the octopus, it is an invitation. The animal shifts position, mantle tightening, skin changing once more to match the speckled brown of the stone. Then it rises above the crab, spreading its arms wide. The webbing that connects each arm unfurls into a canopy, transforming the octopus into a living parachute. In a single motion, it drops over the rock, sealing every edge against escape. This tactic, known as a web pounce, is among the most efficient ambush strategies in the ocean. By enclosing a prey item under its arms, the octopus denies every possible exit. Darkness envelops the crab as the octopus's suckers press down, tasting and gripping all at once. Within seconds, the crab is seized by powerful arms and drawn toward the beak, the octopus's hidden weapon. With crushing force, the beak punctures the crab's armor, injecting venom that paralyzes and begins the slow process of digestion. What began as a simple crack in the reef has become a trapdoor, sprung by intelligence and executed with precision. The parachute strategy would not succeed without the octopus's extraordinary ability to alter its skin. As it spread its arms, the animal flashed colors in rapid succession, ensuring its edges matched the contours of rock and sand until the last possible moment. Chromatophores, tiny sacs of pigment embedded in the skin, expand or contract under muscular control, shifting hues from pale white to deep crimson in milliseconds. Beneath them, iridophores and leucophores scatter light, creating iridescence or diffusing brightness. The result is not just camouflage, but active deception, a performance tailored to the background and the prey. When the octopus drops its net, the crab sees rock until the instant it vanishes into shadow. Sometimes the octopus adds another layer to the trap: tools. After pulling prey from a crevice, it may gather shells, stones, or even fragments of coral to barricade the opening. Divers have observed octopuses building temporary walls around their lairs, using collected materials as both shields and locks. In some cases, they even carry coconut shells across the seafloor, assembling them into portable shelters when danger threatens. These behaviors suggest not only instinct but foresight, the ability to manipulate objects in ways that extend their bodies and their control over the environment. For an animal without bones, this is architecture through improvisation, a flexibility born from intelligence as much as from anatomy. The ecological role of these hunters extends beyond single kills. By preying heavily on crabs and mollusks, octopuses shape the dynamics of reef communities. Crabs that would otherwise graze unchecked on algae are held in balance. Shellfish populations ebb and flow under octopus predation, influencing the creatures that depend on them. And when octopuses themselves fall prey to sharks, groupers, or moray eels, their soft bodies provide rich meals that recycle nutrients back into the food web. Even their abandoned dens, littered with shells from past meals, become microhabitats for smaller creatures. In this way, each octopus is not only predator but engineer, reshaping the reef in subtle but lasting ways. What makes the octopus so compelling is not just its hunting strategy, but the intelligence behind it. Observations in the wild reveal problem-solving behaviors that blur the line between instinct and reasoning. An octopus that fails to extract a crab from one angle may shift approach, probing from another. If arms alone cannot dislodge prey, it may lift and reposition a stone. In captivity, octopuses have been known to unscrew jars, manipulate locks, and even squirt jets of water to short-circuit lights or annoy their caretakers. While such anecdotes can seem playful, they reveal something deeper, a mind capable of exploration, adaptation, and even experimentation. Intelligence in an octopus is not centralized in a brain commanding limbs, but spread through a network of neurons that allows both independence and cooperation. The crab beneath the parachute net had little chance once the arms sealed off the world. Yet it is not only crabs that fall victim. Fish hiding in crevices, snails anchored to rocks, even unsuspecting shrimp are drawn into the octopus's grasp. Each capture reaffirms the adaptability of a predator that does not rely on speed or brute force, but on surprise, flexibility, and strategy. Unlike sharks, which hone a few perfected tactics, octopuses invent solutions in real time, adjusting their approach to each new challenge. This improvisational hunting style is both their greatest strength and the hallmark of their intelligence. As dusk falls on the reef, the octopus retreats once more into its lair, arms curling inward like question marks. Its body fades from the bright contrast of hunting colors to the muted tones of stone. The world outside shifts into nocturnal rhythm, with plankton drifting upward and predators of the night taking their place. But beneath the rock, the octopus digests its meal, conserving energy for the next ambush. Its arms twitch slightly, neurons firing as though rehearsing future hunts. For this is not a predator that repeats blindly. Each encounter, each success or failure informs the next. It is a life lived in improvisation, in the moment-to-moment artistry of survival. The parachute net is more than a tactic. It is the embodiment of the octopus's design. Soft-bodied yet armed with strength, brainy yet decentralized, fragile yet endlessly adaptable, the octopus turns cracks in the reef into trapdoors and moments of opportunity into decisive captures. Intelligence here is not confined to a skull but diffused across arms, skin, and environment. It is a reminder that evolution has written many versions of cunning, and in the case of the octopus, it has written one in 8 directions at once. The reef at midday is a tapestry of shifting colors. Shafts of sunlight filter down through the rippled surface, dancing across corals in hues of gold and turquoise. Schools of damselfish flicker like sparks above the branching corals, while a grouper lurks in the shadows, patient and watchful. In this busy theatre of life, a shape emerges that at first seems like nothing at all, an indistinct smudge along the sandy bottom, almost invisible in its stillness. It is a cuttlefish, master of disguise, lying in wait. But unlike the passive camouflage of a flounder or the static pattern of a stonefish, this animal's concealment is alive, shifting with the light. One flank ripples with the sandy beige of the seafloor, grains and speckles arranged to mimic the randomness of sediment. The other flank, hidden from the grouper's gaze, pulses with electric waves of black and white bands, a strobe of signals directed not at prey, but at another cuttlefish hovering nearby. To the fish, there is nothing unusual, a patch of sand, a blur of reef. To the rival cuttlefish, however, the message is unmistakable. Cuttlefish possess skin like no other. Within it lie layers of specialized cells, each serving a role in sculpting appearance. Chromatophores, tiny sacs of pigment controlled by muscles, expand and contract to produce spots of color, yellows, browns, reds, that can flash across the body in an instant. Beneath them, iridophores and leucophores scatter light, generating iridescence or reflecting ambient colors of the reef. Papillae, muscular protrusions, rise or flatten to alter the very texture of the skin, breaking outlines or mimicking the lumps of coral and rock. Together, these elements create a dynamic canvas that can shift from smooth to rugged, from pale to dark, from background to spotlight in less than a heartbeat. No painter could hope for such speed, and no screen could rival the resolution of living tissue sculpted by evolution into a biological display system. But what sets cuttlefish apart is not just the ability to hide, it is the ability to communicate while hiding. Many reef animals cannot perceive the full range of these displays. Humans, for instance, are blind to the polarization of light. Cuttlefish, however, can both see and produce polarized patterns, subtle alignments of light waves invisible to most eyes. When a cuttlefish pulses bands of polarized light along its skin, a mate or rival perceives the broadcast with clarity, while a grouper or snapper sees only the bland tones of camouflage. This ability allows cuttlefish to maintain a private channel of communication, a secret language overlaid upon the disguise. In evolutionary terms, it is a double-edged adaptation: remain hidden from predators and prey, while simultaneously sending signals to members of one's own kind. It is stealth and broadcast fused into one. Now the cuttlefish shifts its posture. Its body inflates slightly, arms lifting from the sand. Across its flank, the signaling bands intensify, directed squarely at the rival that hovers just out of reach. These signals might be a warning, claiming territory, advertising strength, or perhaps a courtship attempt, weaving patterns that proclaim readiness to mate. On the side facing the grouper, however, the illusion of sand persists. The predator sees nothing more than background noise, a patch of substrate unworthy of attention. This duality, one message for some, another for others, is the very essence of cuttlefish strategy. Control the light field, and you control who understands the battlefield. The grouper, oblivious to the private exchange, drifts closer, its eyes fixed on what it suspects to be a small, edible shadow. But the cuttlefish has been waiting for this. From its folded arms shoot two feeding tentacles, spring-loaded appendages that remain coiled until the final instant. They extend with blinding speed, faster than the blink of an eye, propelled by muscular hydraulics that force fluid into the tentacle sheath. At the tip, suckers grip with vacuum precision, locking onto the grouper's intended prey. In an instant, the fish is dragged into the cuttlefish's waiting arms, where rows of suckers secure it as a sharp beak delivers the decisive bite. To the grouper, the ambush was invisible until the moment of capture. To the cuttlefish, it was a carefully managed play of light, deception, and timing. The mechanics of this strike are as remarkable as its speed. While most predators rely on jaw power or body acceleration, cuttlefish use a dual system. The arms serve as anchors, spreading wide to contain and manipulate, while the tentacles provide reach and precision. Once prey is secured, suction mechanics take over. Suckers lined with chitinous rings create near-perfect seals, ensuring escape is almost impossible. For small fish and crustaceans, the strike is a death sentence delivered in fractions of a second. Yet hunting is only one aspect of the cuttlefish's brilliance. Their ability to manipulate skin patterns plays roles in reproduction, rivalry, and even deception of their own kind. Males, for instance, sometimes employ split signaling, presenting a courtship display to a female on one side of their body while showing a threatening pattern to a rival male on the other. This duality allows them to pursue mating opportunities while deterring competitors, all without revealing their true intentions to both at once. It is a form of strategic misdirection, an animal using its body as a living billboard with multiple messages displayed simultaneously. In the broader ecology of the reef, such abilities grant cuttlefish an edge. They are not large predators. Many fish and marine mammals prey upon them, and their soft bodies offer little defense. But by controlling perception, they flip the balance of power. Camouflage buys time. Polarization signals maintain social bonds without attracting unwanted attention. Rapid strikes ensure that opportunities are seized before rivals or predators intervene. And when necessary, cuttlefish can expel ink, an ancient tactic that serves both as smokescreen and decoy, clouding the water while the animal vanishes into new camouflage beyond. Their role as predators helps regulate populations of small fish and crustaceans, preventing any one group from overrunning the reef. At the same time, they themselves serve as prey for larger hunters, passing energy upward through the food chain. But unlike many reef species, their contribution is not merely numerical, it is behavioral. By influencing how fish respond to patterns of light, shadow, and motion, cuttlefish reshape the very rules of predator-prey interaction. A grouper learns over time that the reef is filled with false impressions. A crab may hesitate at a patch of sand that seems too alive. Through deception, cuttlefish alter the decision-making of countless species around them, inserting themselves into the evolutionary logic of the ecosystem. As the afternoon light wanes, the cuttlefish retreats into the mottled embrace of the reef. Its skin settles into neutral tones, indistinguishable from the rocks and corals surrounding it. The rival drifts away, signals spent, while the grouper vanishes into deeper channels. For now, the performance is over. But the reef remains a stage, and tomorrow the cuttlefish will play again. Sometimes predator, sometimes suitor, always actor in a theater where light and perception are the script. In the end, the cuttlefish demonstrates that survival in the ocean is not only about strength or speed. It is about mastery of appearance, about knowing what others can and cannot see, about controlling the information field that defines every encounter. By sculpting light with their skin, by broadcasting privately while remaining hidden publicly, and by striking with precision in the final instant, cuttlefish embody a strategy both elegant and ruthless. They remind us that in the reef's endless war of perception, victory belongs to those who can draw the lines between signal and silence, between illusion and truth. Control the light field, and you control who understands the battlefield. The tide is low on a shallow reef flat, and the water is glassy and clear. Shafts of sunlight cut through, scattering on the sandy bottom, where corals rise like stone fortresses. Here, tucked inside a narrow burrow in the limestone, waits one of the ocean's most improbable predators. Its body is compact, armored in iridescent plates that shimmer with hues of emerald and copper, a living shard of stained glass. But it is not beauty that defines the mantis shrimp. It is violence compressed into muscle and chitin, waiting to be unleashed. At the mouth of the burrow, a crab ventures too close, claws lifted cautiously as it probes the substrate for scraps. The mantis shrimp remains motionless, eyes swiveling independently atop their stalks, each orbiting like gyroscopes. These eyes, among the most complex in the animal kingdom, can detect not only color but polarization, ultraviolet patterns, and minute flickers of movement invisible to most creatures. Where we see a crab, the shrimp sees texture, polarization contrast, and hidden edges of shell. Every detail is mapped with precision before the strike. Then, with no warning, the shrimp's raptorial club arcs forward. For the briefest instant, there is only speed, so much speed that water itself cannot keep up. The club moves faster than a bullet, accelerating with over 10,000 Gs, a rate of force so extreme that steel would deform under similar conditions. In its wake, the pressure of water collapses, forming a vapor bubble that flashes white before imploding with a sharp crack. The crab's claw snaps cleanly in half, shattered not just by the club's impact but by the invisible second hit, the collapse of the cavitation bubble. Two strikes arrive almost simultaneously, one from the solid limb, the other from water transformed into shockwave. The crab staggers, helpless. The mantis shrimp drags it into the burrow, victory sealed in milliseconds. This phenomenon, cavitation, is at the heart of the mantis shrimp's lethal power. When a limb moves faster than water can refill the space it displaces, vapor pockets form. These bubbles, though ephemeral, collapse with explosive force, generating temperatures as high as the surface of the sun in microscopic flashes of light. For a fraction of a second, a star seems to be born on the reef floor, not in the sky. The collapsing bubble delivers an acoustic shockwave powerful enough to rupture tissue, stun prey, and even crack the glass of aquaria unlucky enough to house one of these creatures without proper precautions. It is an invisible weapon, born not of anatomy alone, but of physics itself, a reminder that predators can harness the properties of the medium they inhabit as weapons. The mantis shrimp's clubs are marvels of engineering. Built not of brittle bone, but of layered chitin and mineralized calcium phosphate, they are reinforced with helicoidal fibers, spirals that distribute stress evenly throughout the structure. This arrangement is strikingly similar to the designs used by human engineers in advanced composites, materials tested for impact resistance in aerospace and armor. Each club can withstand thousands of blows without breaking, even though each strike delivers forces that would shatter ordinary biological tissue. It is not only speed that makes the strike lethal, but the durability of the weapon itself, a living hammer that can be swung again and again without failing. In ecological terms, this weapon allows the mantis shrimp to exploit prey that few others can access. Hard-shelled crabs, armored snails, and even small clams are vulnerable to its blows. Where other predators are forced to abandon such prey or waste energy on prolonged assaults, the mantis shrimp ends encounters instantly. This access to armored prey grants it a niche distinct from other reef hunters, a specialization that links it to the broader ecosystem. By breaking shells, it releases nutrients otherwise locked away, feeding not only itself, but scavengers that benefit from its leftovers. It is, in a sense, both predator and recycler, cracking open the locked vaults of reef life. Yet the mantis shrimp is more than a blunt instrument. Its eyes, mounted on mobile stalks, grant trinocular vision in each eye, meaning that depth can be calculated by one alone. With spectral sensitivity that extends into ultraviolet and the ability to detect polarized light, the shrimp perceives a world beyond our comprehension. The iridescent patterns on fish scales, invisible to us, shine like signals to them. Polarization differences on the surface of a crab shell highlight weak points in armor. Even the shifting angles of refracted sunlight on sand reveal hidden creatures beneath. Vision here is not merely perception, it is targeting, an information system feeding the precision of each strike. The burrow itself is part of the strategy. Carved into reef rock or sand, it provides both refuge and ambush site. From within, the mantis shrimp can survey the outside world with minimal exposure, eyes swiveling above like periscopes. Prey that wander too close find themselves within the narrow kill zone of its strike, a zone where reaction time is meaningless. For the crab that stepped unwittingly near, the moment between safety and destruction was shorter than the blink of an eye. Despite its violent reputation, the mantis shrimp is not reckless. Each strike carries a cost, energy expended, risk of damage, and the need to recalibrate after impact. They do not swing wildly, but choose moments carefully, assessing prey with extraordinary patience. Sometimes they test first, tapping with antennae or probing with subtle motions before unleashing the club. It is hunting as calculation, where speed and strength are only unleashed when certainty aligns. The evolutionary implications of such a weapon are profound. Over millions of years, the arms race between mantis shrimp and their armored prey has sculpted both groups. Crabs evolve thicker claws, snails more convoluted shells, clams denser valves, The mantis shrimp responds with stronger clubs, faster strikes, and more refined vision. Each adaptation on one side triggers refinement on the other, a cycle of escalation that fuels the diversity of forms seen across the reef. In this sense, the mantis shrimp is both participant and driver of evolutionary creativity, shaping not just its own lineage, but the architecture of its prey. The human fascination with mantis shrimp has grown not only from their extraordinary biology, but from the technological insights they inspire. Engineers study their clubs to design new composites, mimicking the helicoidal fiber arrangement to build materials that resist cracking under repeated stress. Their eyes, with their ability to detect polarized light, offer models for advanced imaging systems that could one day detect cancers or improve satellite vision. In the laboratory, as much as in the reef, the mantis shrimp becomes teacher as well as predator, a reminder that evolution's solutions often surpass human invention. As the reef settles into dusk, the mantis shrimp remains hidden in its burrow, claws folded, meal secure. Above, schools of fish drift into deeper channels, and the tide begins its nightly shift. The crab it struck is no more than fragments, consumed piece by piece in the safety of stone walls. But the lesson of the strike lingers. What we see is not always what delivers the killing blow. The club's arc is visible, yes, but the bubble it leaves behind, the flash of light, the imploding force, is invisible to all but the physics that governs it. Prey may fear the strike, but it is the bubble, collapsing silently in the water, that seals their fate. In the end, the mantis shrimp embodies a paradox. Small, often no longer than a human finger, it wields one of the most powerful weapons in nature. Its world is measured not in brute size, but in the manipulation of forces invisible to the eye: pressure, cavitation, and the strength of materials spun from biological spirals. It is a creature that turns water itself into a weapon, a predator whose power lies as much in physics as in flesh. The invisible pressure change hits harder than the punch you see, and in that invisible world, the mantis shrimp reigns supreme. The reef lies in stillness beneath the midday sun, a labyrinth of stone and coral pocked with crevices, caves, and tunnels. Fish hover among branching corals, wary of the shadows that ripple through the water. From the edge of the reef slope, a shape glides into view, slender and fluid, its body marked by stark black and white bands that shimmer against the turquoise backdrop. It is a sea snake, a creature born of land but refashioned for life beneath the waves, threading its body with a deliberate serpentine grace. Each undulation carries it closer to the reef, not in pursuit of open water prey, but toward the hidden world that lies within cracks and holes. Unlike the sharks or groupers that dominate the outer reaches of the reef, this predator does not seek speed or force. Its strategy is rooted in precision and persistence. With its narrow head leading the way, the snake slithers across the surface of coral blocks, tongue flicking rhythmically into the current. The forked tongue, once an adaptation for air, now serves with astonishing sensitivity underwater. Each flick draws in microscopic particles of chemical scent dissolved in seawater. These molecules adhere to the tongue's bifurcated tips, which transfer them to the vomeronasal organ inside the skull. There, the information is passed into a map: where prey has been, which crevice hides fresh passage, and which burrow still carries the fading signature of a fleeing fish. This sensory system allows the sea snake to track targets invisible to vision. A goby hiding deep within a crack may never betray its location by movement, but it cannot mask its chemical trail. The forked tongue, by comparing chemical concentration from left and right tips, delivers directional cues with remarkable precision, like stereo smell. In essence, the snake reads the reef in layers: scent lines hovering in water columns, chemical shadows left on sand, invisible threads of presence woven into the stone. Where most hunters search by sight or sound, the sea snake hunts by smell so fine it becomes a compass pointing into darkness. The snake's body slips downward, buoyancy perfectly balanced. Unlike its terrestrial ancestors, it does not breathe with paired lungs. Instead, evolution has extended a single lung into a long inflated reservoir that runs nearly half the length of its body. This lung is not merely for air storage, but acts as a buoyancy tank, keeping the snake neutrally balanced so it neither sinks nor rises without intent. With gentle adjustments of body posture and lung inflation, it can cruise level through the reef, conserving energy for the precision of its probing. Its nostrils, perched atop the snout, are sealed by valves whenever the snake submerges. A flicker of muscle closes them tightly, preventing even the smallest leak. Salt, too, presents a challenge. In an environment where every gulp of water threatens imbalance, specialized glands remove excess salt, excreting it through the tongue in subtle concentrations. Even the tail holds secrets. Skin on the tips of some species contains light-sensitive cells, a remnant of vision that helps detect shadows overhead. For an animal threading cracks in the reef, this extra awareness may be the difference between safety and the strike of a predator swooping from above. The snake pauses at a fissure, tongue flicking more rapidly now. Something within stirs, the faint tremor of a goby hidden deep in the crack. The snake's head dips, nostrils sealed, and slides into the crevice. Its jawbones, loosely hinged, allow the skull to narrow into spaces that seem impossibly tight. For a moment, only the striped coils outside betray its presence. Then the head emerges again, jaws clutching a wriggling fish. The goby's camouflage and retreat into stone could not protect it from a predator whose sensory suite is tailored for this very task. With a few swift gulps, the prey is swallowed whole, its escape route turned into a dead end by the snake's persistence. Venom ensures that such captures end swiftly. Though sea snakes are among the most venomous reptiles on Earth, their toxins are designed not for defense alone, but for efficiency. A goby, a blenny, or a small eel caught in the jaws of a sea snake can be subdued in seconds, venom overwhelming the nervous system to prevent wasted energy in prolonged struggle. Yet venom is not used indiscriminately. The snake relies first on stealth, on probing crevices, on smell-guiding strikes. Venom is the coup de grace, a guarantee that once captured, prey cannot escape. In evolutionary terms, the sea snake represents a remarkable rewriting of terrestrial anatomy for aquatic life. Its ancestors slithered through forests and grasslands, tasting air for scents carried on the wind. Here, their descendants taste water, decoding the reef's chemical language with equal mastery. Where lungs once carried air for short bursts, one has stretched into a buoyancy device, turning breath into balance. Where scales once gripped earth, the body has flattened laterally, forming a paddle-like tail that propels each undulation with ease. It is a land sensor suite, rewired for reefs. The ecological role of the sea snake extends beyond the individual strike. By specializing in small cryptic reef fishes, they regulate populations that might otherwise overgraze algae or disrupt coral balance. Their presence forces prey to alter behavior, driving gobies deeper into burrows, blennies further into weed patches, reshaping patterns of competition among reef residents. And as prey themselves, snatched by sharks, sea eagles, or larger predatory fish, sea snakes pass their own energy upward, linking the concealed world of reef cracks to the open water predators patrolling above. Despite their formidable venom, sea snakes are not aggressors toward larger animals unless provoked. Divers who encounter them often note their curiosity, snakes that swim near to investigate, tongues flicking as they taste the chemical wake of an unfamiliar intruder. Their movements are graceful, almost mesmerizing, each undulation writing calligraphy across the reef. Yet beneath this elegance lies a predator's efficiency, one that survives not by speed or size, but by probing the overlooked spaces others cannot reach. The reef at dusk becomes a shifting mosaic of colors as the sun drops low, shadows lengthening across the corals. The sea snake continues its patrol, threading through channels, pausing at fissures, tongue flicking like the ticking of a clock. Every crevice could hold prey, every burrow an opportunity. It does not need to see its quarry, only to taste the molecules drifting invisibly through the water. Where others rely on light, the sea snake thrives in the unseen. Its hunt is a reminder of how evolution reshapes familiar forms into something entirely new. A snake, once bound to land, has become an aquatic predator tuned to the physics and chemistry of the reef. It does not sprint across sand or coil around branches. It flows like water, reading a hidden world through a tongue that smells direction. through a lung that balances buoyancy, through skin and glands that filter salt and sense light. It is a hunter of holes, a predator whose mastery lies not in dominating open seas, but in owning the narrow corridors of stone and sand. And so the goby vanishes, the snake glides onward, and the reef absorbs the moment as though nothing had happened. Yet within that brief strike lies an entire narrative of adaptation, land-bound senses transformed, anatomy rewritten, survival redefined. In the ocean, victory does not always belong to the largest or the fastest. Sometimes it belongs to the one who can read what others overlook, the scents drifting in water, the faintest chemical whispers, the hidden lives tucked in cracks. For the sea snake, the reef is a book written in molecules, and with each flick of its tongue, it turns the page. The reef slope dissolves into a plain of pale sand, its surface broken only by scattered shells and the faint shadow of drifting seagrass blades. At first glance, it is an empty stretch, unremarkable in its stillness. But the sand holds secrets. A patch near the base of a coral head shifts almost imperceptibly, as though the seabed exhaled. Then, with the suddenness of a sprung trap, the surface erupts. A stingray bursts upward, wings unfurling in a wide arc, and a startled fish, attempting to flee, bends inexorably toward the center of the disc, pulled not by teeth or claws, but by an invisible force. In less than a heartbeat, it is gone, consumed by hydraulics more than muscle. Stingrays are predators defined by the mastery of physics rather than brute aggression. While their cousins, the sharks, rely on bursts of speed and serrated teeth, stingrays exploit the properties of water and sediment, engineering ambushes from invisibility. To bury themselves, they do not simply flap downward into the sand. Instead, they use spiracles, small openings just behind the eyes, that draw in water and expel it through gill slits on the underside. By forcing jets beneath their bodies, stingrays fluidize the sand, suspending grains in turbulent currents that behave more like liquid than solid. This allows the ray to sink seamlessly, vanishing beneath the surface until only faint outlines remain. In seconds, the plain appears empty once more, the hunter hidden in a layer no thicker than a shell's width. This burying tactic serves dual purposes, defense and predation. Hidden beneath sand, the stingray is shielded from larger predators while simultaneously poised to ambush unsuspecting prey. It is not simply hiding, it is reconfiguring the battlefield. Prey fish, conditioned to associate shadows with danger, see nothing above them, no looming form to trigger flight. Instead, they cross unknowingly over a predator lying in perfect silence below, blind to the fact that the very ground they trust is alive. The strike, when it comes, is not a matter of muscular jaws but of hydraulics. Stingrays feed by suction, a process far more efficient than the bite and tear strategies of most carnivores. When the mouth expands rapidly, the buccal cavity creates a sudden drop in pressure, drawing water and prey inward faster than muscle alone could pull. For small fish and crustaceans caught in the path, resistance is futile. They are dragged toward the center by water itself, funneled into the stingray's mouth, as though by a string pulling from within. The prey is not captured by strength, but by physics, a predator turning the medium it inhabits into its ally. The fluid dynamics of this feeding strategy make the stingray a formidable hunter in environments where speed would be wasted. Small benthic fish dart unpredictably, vanishing into crevices at the first hint of pursuit. Crustaceans bury themselves, relying on their own use of sediment for concealment. Against most predators, such strategies succeed. Against the stingray, they fail. By turning sediment and water into tools, stingrays outmatch the very defenses their prey have evolved. What hides in sand can be flushed out by spiracle jets. What flees into open water is caught by suction before escape begins. But stingrays are not only ambush hunters. When they glide across the seafloor, their wide pectoral fins generate vortices along their edges, streams of water that curl and spiral in controlled patterns. These vortices create both silence and agility. Unlike the thrashing tails of many fish, which produce turbulence detectable by lateral lines of prey, the stingray's motion is nearly noiseless, a glide so smooth that fish sense nothing until too late. And when sudden lift is required, the those same vortices provide the boost, transforming a slow drift into a rapid surge. For prey, the ray seems to appear out of nowhere, rising from beneath the sand or gliding with ghost-like stillness before exploding into action. The most iconic feature of stingrays, the venomous spine on their tails, is often misunderstood. While it can serve as a defense, lashing out when predators or humans press too close, it is not their primary weapon. The spine is serrated, barbed, and coated in venom-laden tissue, capable of inflicting severe injuries. But in the calculus of stingray survival, the spine is insurance, not strategy. Their true mastery lies not in the threat of venom, but in the manipulation of their environment, the burying jets, the suction strike, the vortex glide. Predation is solved with physics, not with stingers. The ecological role of stingrays reveals even deeper complexity. By disturbing sand to bury themselves or flush prey, they aerate sediments, cycling nutrients into the water column and reshaping microhabitats for countless invertebrates. Their feeding pits, left behind after strikes, become oases for smaller organisms, attracting scavengers and altering patterns of distribution across the sea floor. In this way, stingrays are not only hunters, but engineers, reshaping ecosystems with every breath of sand. Stingrays also reveal the elegance of evolutionary compromise. They are cartilaginous fish like sharks, but their bodies have diverged radically. Flattened forms, wide fins fused into discs, spiracles shifted to the top of the body. These changes suit life along the benthos, where ambush replaces pursuit. Yet despite these modifications, rays retain kinship with their shark relatives, sharing electroreceptive organs known as ampullae of Lorenzini. These allow them to detect faint electrical signals from prey, a heartbeat beneath sand, a muscle twitch in the darkness. Combined with suction feeding, electroreception ensures that even prey attempting stillness cannot escape detection. For the small fish that wandered over the buried ray, every defense was undone in moments. Its vision did not detect danger above. Its lateral line did not register turbulence approaching. Its muscles did not react quickly enough to the drop in pressure. Physics itself conspired against it, turning its own environment into a trap. For the stingray, this efficiency means survival with minimal effort. It does not chase tirelessly or expend energy on pursuits doomed to fail. Instead, it waits, perfectly balanced between invisibility and inevitability. From a human perspective, stingrays often appear placid, even gentle, gliding gracefully across aquaria or shallow lagoons. Yet this calm exterior masks a precision hunter whose strategies are as refined as any in the ocean. Their power lies not in aggression, but in their ability to rewrite the rules of engagement. Sand is not just substrate, it is cloak. Water is not just medium, it is weapon. Fins are not just for motion, they are wings that bend currents into silence and sudden acceleration. As the tide shifts and the reef begins to hum with the stirrings of evening, the stingray settles once more beneath the sand. Spiracles pulse softly, jets of water fluidizing the grains until the body disappears, edges blurred into the seabed. To any passing fish, the patch of sand is just another blank stretch, lifeless and safe. But hidden beneath lies a predator that has mastered the physics of its world. The next fish to wander overhead will find that safety was an illusion, undone not by teeth or claws, but by pressure, suction, and lift. In the stingray, we are reminded that survival in the sea is often won not by spectacle, but by subtlety, by the mastery of forces too invisible to notice until the moment they strike. To the prey, the seabed exhaled, the sand betrayed them, the water itself pulled them in. To the stingray, it was simply physics made flesh. Master the seafloor's physics, and the prey never sees the strike.